Okay. Now let's continue on serializability. A serializability of schedule is used to find non-serial schedules that follow the transaction of execute concurrently without interfering with one another. It identifies which schedules are concurrent when the execution of transaction have intervening of the operation. A non-serial schedule will be serializable if and only if as follows in A and in B. Let's see this. Transaction 1 is here, transaction 2 is here. Here transaction 1 is there, transaction 2 is there. In transaction, it takes the time. Here read A is equal to A minus N, write A, read B is equal to B plus N, write B. In transaction T2, read A is equal to A plus M, write A. In B figure, here with the time slash, that means here the initial read is there, and after time slash, what happening? That means during this time, T2 is under transaction. That's what we have seen in the previous figures. That is in serial schedule and non-serial schedule. So seriability is used to find non-serial schedules and to execute concurrently without interfering with one another. So this is the diagram. So in this time, read A is there. A is equal to A plus 1 M, write M. So here this type of transaction has been credited. Here in after time little time slash, read A is equal to A minus N, write A, read B is equal to B plus N, write B in schedule B. In schedule C, in the first initial time slash, read in for T1 state, read A is equal to A minus 1, and in next time slash T2 is coming, read A is equal to A plus M. After this, write A, read B, write A. In transaction T2, B is equal to B plus N, write B in transaction T1. So this is schedule C. Next, in schedule D, let's see the transaction. Read A is equal to A minus N, and write A. Again, there is a time slash gap. Read B is equal to B plus N, write B. In this gap, transaction T2 takes place. That is, read A is equal to A plus M, write A. So, schedule A and schedule B are serial schedules. Schedule C and Schedule D are non-serial schedules, as we have discussed here in the previous slides. So unless we understand serial, non-serial, the combination of this leads to serializable schedule in concurrent processes. So state 1 and state 2. In state 1, there are two transactions, T1, T2. Read A, write A, read B, write B. In transaction T2, read B, write B, read A, write A. In schedule 2, transaction T1 and transaction T2, read and write. Here, again, there's a gap. Read B, again gap. Again, what is this gap? This is called a time slash. So write B. In this time slash transaction 2, the initial T1 transaction, so there is a time slash in transaction T2. After that, read B, write B, time slash, read A, time slash, write A. We cannot change the sequence of the statement execution, but we can go for context switching as shown above. So this is called context switching. When it is coming here, during this it comes to T2, again coming here, again this is called context switching. No multiple instructions are executed because processes do not execute multiple execution at the same time. Does process do more than one task? Yes, let's see for that. Serial scheduling with no context switching, non-serial scheduling with context switching happening. So the state 1 can be defined to state 1 as follows. So read A, write A. Next in transaction T2, read A, write A. Read B, write B. In transaction T2, read B and write B. So this can be converted to read A, write A, read B, write B. So after this time switching, context switching, read A, write A, read B, write B in this state of T2. If we cannot convert the non-serial schedule to serial schedule, then we can say it is a consistent schedule. But we cannot convert non-serial to serial schedule. It does not mean it is inconsistent. It is not guarantee that the student not passing MSET is poor. If we swap instructions of two transactions, then we call them as non-conflicting instructions, otherwise called as conflicting instructions. There is a clash. That is called a clash instruction or conflicting instructions. So we can swap instructions of non-serial schedule to make it serial schedule by swapping on non-conflicting instruction. First, we should find out when the instructions is conflicting and when the instruction is not conflicting. We have to identify this. So here transaction T1 and Tj. Here read and write. There is no conflict. There is no problem. Here T1 and Tj. First write is there in the time slash, then read A. So there is no problem. Here again T1, Tj, both are read statements but not time slash has no conflict. So no problem. Here the T1 and Tj, read and write is happening at the same time slash. Again, write and read is happening at the same time slash. Again, the problem arises. Problem here also. So write, read, read and write. Here, if problem exists means the statement is conflicting, so no swapping can be done. If write and write happening, and it is called blind writing because they are not reading at all. Here both are writing and both are reading. Here all is writing. This is called a blind writing. Instructions are said to be conflicting when they belong to different transactions, but they must operate on same data value, and one of the instructions should be a write instruction. Let's click to add some text here. Here the state has transaction T1 and T2, read and write read B and write B, read B and write B. Yes, two states, that is S1, S2, and the transaction is T1, T2. So this is one state, and this is one state which is linked to this state, and this is the state of red line. In this one, read and write is one state. It is get overlapped with read and write. Again, read and write, again overlapping here. So let's see what it means. So this is called conflicting serializability. So non-serial schedules are changed to serial schedule by swapping of non-conflicting instructions. Then we say it is a conflict serializability. So it is consistent. So the table here is read of A, and whether it is no, yes. Let's see the status. Read, write, no. Read, write, yes. That means read of A, write of B. We cannot do two different. So no. Read of A and write of A. So this comes under same. So A, yes. Write of B and write of A, no. Write of A and read of A, yes. We can do this because it both belongs to A state or A module. Let's see the transaction of T1, T2, T3. Here step 1 is here T1, it goes to here and here. Next, T1 goes here and this is step 2. Here what we see is T1 goes this place and coming to this state. So this is state 3. But here this one, T1 goes to T3 and T1 goes to T2 and T3 goes to T1 and T3 also goes to here a ring is followed. That means it comes here. It is called a loop. So let's see what is this loop or a cyclic means. Okay. Next, here read of X, T root T3 nothing. Again, the second time slash T1 T2 read of Z. Again, in third slice, T1 nothing, T2 nothing. Transaction of write is going on. The here in T1 nothing is there. T2 read of Y and no transaction. Here read of Y nothing and nothing. Here T1 nothing. W of Y is there, and that is W means right here. R is for read and blank is no time slash, no swapping is going on. Swapping is not, conflicting is not going on here, and time slash is there. So that is mean. So nothing means time slash. So here is nothing. T1, T2 is nothing, and the 3 is right operation. Same here. T1 nothing, T2 is right of Z, and here is nothing. So right of X and nothing. Cyclic, so not a conflict serialization. Inconsistent cannot convert not serial to serial schedule. So again, coming to the next slide, here T1 directly go and meets directing to transaction T3. That is step number 1. T1 directly going to T3. Okay. The next one is T1 going to T2 and changing the state of T3. That is step 2. Here T1 changing the state of T2 transaction. Again, the transaction T1 is also stimulating T3 and T3 is stimulating T2. It is a conflict serialization, non-cyclic, so consistent. But it is a conflict serialization. So let's see the table. T1, T2, T3 are the transactions. R is a read and W is a write. Read of X, nothing and nothing. Here, time slash uh, read of Y and time slash read of Y, time slash write of Y and time slash write of X, time slash and WFX. Here time slash read of X and read of time slash W of X and time slash. Here again, so the different states and different conditions. So what all that we are seeing with the help of this pictorial representations. So the transaction one is T2 in step one, and in step two, transaction one is T3. Transaction one is again going to the state of T2. Here, transaction one is going to T3. Transaction one is going to T2, and T2 is again going to T1. So cycle is there. Again, T1 transaction going to T3, T1 transaction going to T2, and T2 transaction going to T3 and also to T1. That is step 4. Your cyclic, so no, not a conflict serialization, inconsistent. Same here. This is a transaction 1, transaction 2, and transaction 3. That is T1, T2, T3. Read of B dash dash and time slash read of C, read of A dash 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 write of A. So in T2 transaction, in T1 transaction, write A, in T2 transaction, write B, and in the T3 transaction, write A, and in T1, write B. Again, there is a time slash and time slash. Here, nothing, nothing, and write B, nothing, nothing, and write C. So example 1 and example 2. So let's see the example. Transaction T1, T2, and T3. So read of A. So no, nothing is happening here. Here nothing is happening, nothing is happening. In transaction T3, write of A. And in T1, nothing is happening here. Read of A, nothing. So read of A, write of A, and nothing is happening. In T1, write of B, T2, nothing is happening, T3, nothing is happening. At that time slash, at T1, nothing is happening, but T2, write of B, and T3, write of nothing is happening. Here T1 nothing is happening, nothing is happening here in T2 and T3 right operation is going on. And in T1 nothing is there and your right operation of C and time slash that is not, there is a gap. There is a time gap here. Again, right of A, time gap and time gap. And T1 nothing is here. T2 is right is there and T3 nothing is there. Same T1 nothing is here, T2 nothing is here and T3 right B. Here T1 nothing is here, T2 nothing is here and T3 is right C. Here let's see the example 2. Read of operation nothing nothing. Here there is transaction T1, T2 and T3. So nothing, nothing, write B. Nothing, read of B, nothing. Write of A, nothing and nothing. So transaction T1, nothing. Write of B, nothing. Here nothing, nothing, write of C. Write of B, nothing and nothing. Here time slash, read of C and time slash. Read of A, time slash, time slash. Time slash of T1 and T2 right of C and nothing. Time slash of T1 and T2 and right of A. Read of A time slash and time slash. Next, what is concurrency in DBMS? Here, the concurrent execution, the topic is concurrent execution. So before that, we are going before concurrent execution, we have to know what is concurrency in DBMS. Database concurrency is the ability of the database to allow multiple users to affect multiple transactions in the same time. This is one of the main properties that separates a database from other forms of data storage like spreadsheets. Other users can read the file but may not edit data. What is the need of integrity and concurrency in control in DBMS? To handle these conflicts, we need concurrency control in DBMS, which allow transaction to run simultaneously but handles them in such a way that so that the integrity of data remains intact. In the multi-user system, multiple users can access and use the same database at one time, which is known as a concurrent execution of the database. It means that the same database is executed simultaneously on the multi-user system by different users. Reasons for using concurrency control method in DBMS is to apply isolation to mutual exclusive algorithm between conflicting transactions to resolve read, write, and write conflict issues to preserve database consistency through constantly preserving execution obstructions. Advantage of concurrency: reduce waiting time, response time, or turnaround time, increase throughput and resource utilization. If we run only one transaction at a time, then the asset property is sufficient, but is possibly then when multiple transactions are executed concurrently, then database may become inconsistent. Next, what is concurrent example? Example of concurrency is the tendency for things to happen at the same time in the system. For example of the concurrency at work, parallel activities that do not interact has simple concurrency issues. It it is when parallel activities interact and share the same resources, then concurrency issues becomes very important. Purpose of concurrency is to enforce isolation, to preserve database consistency, to solve read, write, and write conflicts. Concurrency control techniques are lock-based protocol, two-phase locking protocol, timestamp ordering protocol, multi-version concurrency control, validation concurrency control. Now let's go to each and every protocol of concurrency. Lock-based protocol. In this type of protocol, any transaction cannot read or write data until it acquires an appropriate lock on it. There are two types of locks, shared lock and exclusive lock. What is shared lock? It is also known as read-only lock. In the shared lock, the data item can only read by the transaction. It can be shared between the transactions because when the transactions hold the lock, then it cannot update the data on the data item. Exclusive lock. In the exclusive lock, the data item can be both reads as well as written by the transaction. This lock is exclusive, and in this lock, multiple transactions do not modify the same data simultaneously. If all the locks are granted, then this protocol allows the transaction to begin. When the transaction is completed, then it releases all the lock. In all the locks are not granted, then this protocol allows the transaction to roll back and waits until all the locks are granted. This is called lock compatibility. So this is a locking system, and S is the state and X is the compatible of transaction. These are some permutations and combinations to see the states of the lock. The lock attained at the time T1. At T2, the lock is released. This is the time slash. Here, exclusive lock. Here, the transaction 1, lock read of B, B minus some transaction going on, write of B unlocked. During that time, transaction does not do anything. At the shared lock, lock of state of B, read of B, unlock B. Note, any number of transactions can hold shared lock on one data item only. Exclusive lock can be used by one transaction at a time. Conversion of locks, upgrading read lock, write lock, downgrading write lock and read lock. Two-phase locking, that is called two-phase locking, 2PL. The 2PL locking protocol divides the execution phase of the transaction in three parts. The first part, when the execution of the transaction starts, it seeks permission for the lock it requires. The second part, a transaction acquires all the locks. The third phase is started as soon as the transaction releases its first lock. In the third phase, the transaction cannot demand any new locks. It only releases the acquired lock. So at the transaction, this is the time axis, and here is the lock is attained, and the lock is released at T end. T begin and T end. So we can see here the two phases are here. There are two phases of 2PL. Growing phase. In the growing phase, a new lock on the data item can be acquired by the transaction, but none can be released. Next, shrinking phase. In the shrinking phase, existing lock held by the transaction may be released, but no new locks can be acquired. In the below example, if lock conversion is allowed, then the following phase can happen. Upgrading of lock from state A to X of A is allowing in growing phase. Downgrading of lock from X of A to S of A must be done in shrinking phase. So here is a growing phase, here is the lock point, and this is the shrinking phase. So this part is called the locking point. So example of lock of state A, T2 transactions, nothing is here. TA at that time, T1 does not exist, and lock of state A. Here again, after that lock of X of B, here T2 transaction nothing, and here both are transactions nothing, unlock A. So T2 nothing is here, so nothing is here, lock of X of C, unlock of B, nothing is here. So nothing is here in transaction T1, but in T2 unlock A. Here T1 nothing is happening, unlock C. So nothing is happening in both the transaction, the ninth state. The following may shows how unlocking and locking work with two-phase lock. Transaction T1, growing phases from step 1 to 3, shrinking phases from step 5 to 7. So this is like this. So step 0, 1, 2, 3, 4, 5. So this is nothing but the steps. So shrinking phase is 5 to 7. Lock point is at 3. Transaction T2. Growing phase is from step 2 to 6. Shrinking phase is from 8 to 9. Lock point is at 6. Let me show this again. So you see this. Strict two-phase locking. The first phase of strict two-phase locking is similar to two-phase locking. In the first phase, after acquiring all the locks, the transaction continues to execute normally. The only difference between two-phase locking and strict two-phase locking is that strict two-phase locking does not release the lock after using it. Strict two-phase locking waits until the whole transaction is committed, and then only it releases all the locks at the time. Strict two-phase locking protocol does not have shrinking phase of the lock. It is a sudden drop when it is released commit. Variations of two-phase locking protocol. As shown in the for strict two-phase locking, this is shown in the figure. Lock is attained and the release at coming. T begins and T ends and time. Variations of two-phase locking protocol. Conservative static two-phase locking acquires all locks before it starts executing. Releases all the locks after commit. Deadlock is freer. Strict two-phase locking only executes locks cannot be released till commit executes. Deadlock may occur. Rigorous two-phase locking, both shared and exclusive locks are not released until transaction is committed, but acquires locks as and when acquired. Deadlock may occur. Timestamp ordering protocol. The timestamp ordering protocol is is used to order the transaction based on their timestamp. The order of transaction is nothing but the ascending order of transaction creation. The priority of the older transaction is higher. That's why it executes first. To determine the timestamp of the transaction, this protocol uses system time or logical counter. The lock-based protocol is used to manage the order between conflicting pairs among transactions at the execution time. But timestamp-based protocols start working as soon as transaction is created. Let's assume there are two transactions T1 and T2. Suppose the transaction T1 has entered the system at 7 o'clock times and the transaction 2 has entered 9 o'clock. T1 has the higher priority, so it executes first as is entered the system first. The timestamp ordering protocol also maintains the timestamp of last read and write operations on the data. The timestamp-based protocol is to avoid conflicting during the execution of the transaction. When multiple transactions are handled by the system and if it is overcrowded, then we need to think of a mechanism to handle the situation. It is like we went to sweet shop to buy hot jamun and the number of jamun prepared is less than the number of people asking for it. So what can we do is instead of making every time to ask for a sweet, but wait till it is prepared, whereby lot of crowding happens, we can easily maintain the situation by allotting a token with a number. But if numbers are used, they are will be confusion on the following days. So we may start with number one on the next day. The same can be applied to temples where people want to see the god like Tirupati. Then it may so happen that the time required with will be a day or 2 or 10 days also. But instead of making the people to stay and stand in a queue, we have assigned with the time brand. This time band is a concept used in the DBMS where we call it as timestamp. The timestamp will, or a time slash also we can tell. The timestamp will be given for the transaction that enters the system for execution. This timestamp is a time of the clock in the system, including date part. So when such a timestamp is given, it will be always unique. So data time never repeats. The system gives the timestamp for transaction and also the timestamp for the data item on which the operation is happening. So this is not the same. So timestamp for us is our date of birth. The transaction enters the system at 10 o'clock on the date, then the timestamp will be according giving as 21 is to 5 is to 2021 is to 10 is to 10 is to 0 is to 0. That is, it is seconds, minutes, hours, next week, uh, day, and year. And if the transaction performs the operation on data item Q at 11, then the transaction will be 21 is to 05 is to 2021 is to 11 is to 00 is to 00. So TI request for read of Q. If T, yes, timestamp of TI is less than the write of T as timestamp of Q, means TI needs to read the value of Q that was already overwritten. Hence, request must be rejected and TI must roll back. If timestamp of T1 is greater than equal to write of timestamp of Q, operations can be allowed. So let's see in this swapping to avoid the confusion. There is TI timestamp is equal to 5, TX timestamp is equal to 10. Here, read of Q has missed this slot. then Tx is vacant. Here again Ti is vacant here, right of Q. Not allowed here as there is read of Q. Again, there is a gap in the time slash. So time slash is there is vacant here, and the case. If it swap, then conflict instructions write and read on Q. Same here. Let's see if T times Ts of T1 is greater this condition. So of write of Ts of Q here Ts is equal to 12 and Ts is equal to 10. Here both there is a time slash. Again here Ti of time slash. Again there's a gap here with right of Q. So you only read of Q and a gap. Here again a gap. Here second case allowed your request to is after write operation. If Ts of Ti is equal to right of Ts of Q. Here Ts means time slash. Okay, next. Ts is equal to 10 and Tx is equal to Ts is equal to 10. So both is having no operation here. Again, there is no operation in Ti at this instant, but the Tx instant, there is right of Q. Again, in Ti, there is no transactions or no operation here. Again, there is read of Q. Both are no operations here. T of S of Ti is equal to right of Ts of Q will be equal only when the same transaction as performed write operation and then read operation, but forget the read operation. So read of Q is allowed here because no transaction T1 will be the same, Ts will be the unique. Ti request to write of Q. If Ts of Ti is less than read of Ts of Q means value of Q that is Ti is producing was needed previously and the system assumed that the value could never be produced, hence reject and roll back. If Ts of Ti is less than right of Ts of Q, not allowed. Ti is equal to 5 and T of X is equal to 10. Then here W of Q requested but not performed. Here there is no operation. Again in Ti there is no operation. Read of Q operation is going on. Here write of Q is not allowed and there is no operation. It is swaps of conflict instructions. Write and read on Q happens. If Ts of Ti is less than right of Ts of Q, then when Ti is 5 and Tx is 10. So right of T is supposed to happen here. Here a T of X, nothing is happening. Here T of I of 5, here nothing, no operation. But right of Q is happening in Tx of 10. Again here Tx of 5, Ti of 5, right of Q is not allowed here and Tx of 10 is has no operation. Remaining two cases, the transaction is allowed. Ts of Ti greater than equal to Ts of Q and Ts of Ti greater than equal to right of Ts of Q. These two operations are being allowed and being performed. So we can say that timestamp protocol says that juniors are allowed, but not the seniors allowed to do mistakes. Example, you went to the college gate and started doing something and for which other students ignored it. But if the same activity is done by the professor of the college, then others will laugh and say something and so on. Problems with concurrency, dirty read problem, unrepeated read problem, phantom read problem, lost update problem, and write conflict problems. Let's understand what is the T-read problem. Is in database with an example. Imagine there are two friends who's going to write exams and a friend of X is poor in studies when compared to Y. So X decide to copy the content from X in the examination hall. So during the exam, X allows Y to copy the content, and then once Y completes writing examination in the sense all the answers in all the questions, he decides to give the paper to the faculty thinking everything is done. So the results is announced. Y fails in the examination and X passes the examination with good marks. So you're able to understand the problem here. Imagine there are two friends who's going to write exams and the friend X is very poor in studies when compared to Y. So X decides to copy the content from Y in the examination hall. So during the exam, so X decide to copy the content from X in the examination hall. So during the exam, X allows Y to copy the content. And then once Y completes writing exam in the sense all the answers to all the questions. Here it decide to give the paper, the faculty, and then once Y completes writing examination in the sense all the answers to be answers to all the problems. He decides to give the paper to the faculty thinking everything is done. So the results of announce Y fails in the examination and X passes with good marks. So now Y thinks why he got less marks in the exam when he has copied all the answers from Y only. When he asks the question to X, the X explains that after you left the examination hall, when I was going through all the answers and modified most of them, so the difference. Mm, So what is a mistake done by Y? He should not, he should have submitted the answer sheet after X submits. Then this will not happen. So this is also one of the great lesson in our lives also. Usually children do this. Oh, initial, let's not discuss something in deeper, that's all the personal views. But this type of state happening in this examination halls. Initial value of A in database is 10. Dirty read problem. There are two transactions T1 and T2. A is 10, that is read. A is equal to A plus 1 is equal to 11 because 10 plus 1 is 11. Write A. Now, T2 transaction, nothing is going on at this instance. Now, at this instance, the next instance is T1, nothing is taking, but read of A is there. The next comment is 30, read here, comment is there. Value of A in 11, which is not a permanent value, uncommitted values of A. So here you see the time, here nothing is there, but here T1 performs some operations and then here T1 performs some operations and then commits the transactions. So some operations are performed. So some operation A, B, C, some 1, 2, 3 operations. But at this T2, nothing, no operations are there. And here the commit operations are there. So see, he has committed before and later till then he did not submit anything. So this is the case of X and this is the case of Y. If T1 rolls back the transaction, then so value of A will be back with 10. So to avoid the problem of dirty read, we need T2 to commit a transaction after T1 commits. T2 cannot commit because he has committed. So this is the state. So the example is very beautiful. Better not follow this. Next, unrepeated read problem. Again, the story is there. One day, a younger guy sees the parents are going out, and because of that, he feels very happy. Uh, and in this happiness, he's tried to do something, thinking that he's only present in the home. So he thinks of cooking Maggie and want to watch a Cartoon Network. In this process, he takes Maggie packet and cooker to cook the same. He puts the cooker on the gas stove and then goes to watch cartoon. When he comes back after 10 minutes and he takes out the lid of the cooker, he observes that the cooker contains rice with rajma and not Maggie. In this anger, he tries to throw the rice ball out, and when doing so, he gets a voice of something sitting in the fan saying, "It's me. I want the rice with rajma." Story ends here. So what we want to understand here, he is thinking that he's alone, but he's done something without knowing that there may be a ghost in the house. In the same case, when we run any transaction, every transaction feels that is getting executed and no other transactions are in process. And no will be no transaction. So same here, transaction T1 and T2, X is 10, X is 10, and X is equal to X plus Y. So let's see here, T2 is confused because the two reads, it gets different values of 10 and 15. It will not understand why this is happening, and every transaction feels that is the only transaction working in the system. Same like the ghost in the house. So read operation, T2 nothing is happening here. In T2 nothing is happening, read of X. Write of operation is there, nothing is happening in T2. And the T1 nothing is happening here, and the read of operation. So some instructions are going on, some instructions are going on. So this is how we have to represent this. The phantom read problem. Parents of the boy explains that there is nothing like ghost and all it is your thought. As said earlier, there's a boy sees that his parents are going out and then he tries to do something in the kitchen and he takes the cooker and the pasta packet and cooks the same by placing it in a gas stove, and with the ounce of doubt, then there is a ghost in the house. The boy again goes and watches the cartoon now, but when he goes back to the kitchen after some time, he observed that there is nothing in the kitchen. Phantom read problem. Initial value of x is equal to 10. T1 reads the value of x, which is 10. T2 reads the value of x, which is 10. Then T1 deletes x. T2 now tries to read the value of x. Then he finds that the particular variable does not exist. This is called phantom read problem. Reading a value after it is deleted. So let's see in this time slash. T1 is a transaction and T is another transaction. So read of X, the T2 transaction is nothing here, and the T1 transaction is nothing here, and read of X. Here both T1 and T2 has no transactions, and here but T1 delete operation is going on, and T2 no operations are going on, and here at the next stage, the no operation is going on, the read of X, and the last no operation is going on. So that is what is explained here. Lost update, write conflict. So these are all the algorithms, So T1 transaction and T2 transaction. Let's go to this, and after we can go to this part, okay? The read operation of T1, T2, nothing is there. Write of operation of A, and nothing is here. And nothing is here, write of operation. And write of nothing, no operation, and commit is here. So no operations in this two state, this time slash, and their T1 commit is there. First, this T2 has been committed, and later the last state, the commit. And this is the nothing, no operation is there because it's already committed, so no operations will be there automatically. So value of A is equal to 10. Then A is updated in A is equal to A plus 5. So A is 15. Thinking that A is 15, it will perform commit operation. Okay, a commit operation. But what is the value written in the database? It will be 50 and not 15. So the value of T1 wants to write is not stored in database. This is called write conflict or lost update. At the same time, let's see the transaction of T2, what's happening. T2 without feeding the value of A will modify A as 50 and commits. Without reading the value of A, without reading the value, if it is written, then it is called a blind write. Validation based protocols. Okay, so till now we have seen the timestamp based protocols, log based protocols, testing for serialization, what are the different tests going on. Next, validation based protocols. So validation phase is also known as optimistic currency control technique. In the validation based protocol, the transaction is executed in the following three phases: read phase, validation phase, and the write phase. In this phase, the transaction T is read data from database and executes the operation. It is used to read the value of various data items and stores them in a temporary local variables. It can perform all the write operations on temporary variables without an update to the actual database. Validation phase. In this phase, a temporary variable value can be validated against the actual data to see if it violates the serializability. So write phase, if the validation of the transaction is validated, then the temporary results are written in the database and the system, otherwise the transaction is rolled back. We have seen before also the same. But this also comes under validation process. So we are going to this a little knowledgeable. So validation phase is also known as optimistic concurrency control technique. In the validation based protocol, the transactions executed in the following three phases: read phase, validation phase, and write phase, as we have seen here. This protocol is called, the next protocol, this protocol is called the optimistic protocol because it is continued execution of the statement, thinking that everything will finish without any problem. This protocol maintains three timestamps: timestamp at start of the transaction, timestamp at the validation phase, finish timestamp at the end of the write phase. This leads to starvation in the system as the transaction has to be rolled back every time the validation fails. And once again, we have to start the fresh transaction. There is no chance of deadlock as we are using timestamp to check for serializability of the schedule and so on. This protocol is also called optimistic protocol, as we have seen in the previous, in the same slide. Multiple granularity. So, multiple granularity start by understanding the meaning of granularity. Granule Granularity is the size of data item allowed to log. Multiple granularity. It is defined as hierarchical breaking up the database into blocks where it can be logged. So this leads to the concept called blockchain. The multiple granularity protocol enhances concurrency and reduces log overhead. It maintains the track of what to log and how to log. It makes it easy to decide either to log the data item and to unlock the data item. This type of hierarchy can be graphically represented as a tree. For example, consider a tree which has 4 levels of nodes. The first level or highest level shows the entire database. The second level represents the node of type area. The highest level database consists of exactly these areas. The area consists of children nodes, which is also called as files. No files can be present to more than one area. Finally, each file contains child nodes known as records. The file has exactly those records that has its child nodes. No record represent is more than one file. Hence, the levels of the tree starting from the top level are as follows: database, area, file, and record. In this example, the highest level shows the entire database. The levels below are file, record, and fields. So this is the hierarchical tree of for the multi-granularity. There is a base database which is having children A1 and A2, and A1 is having A, F, B, and FC and FT for AZ, and A2 and FA is having RA1 and RA, yeah, and this is B1 and RBN, and so on till RBN. If this link is cut, if this link is cut, the whole data has been collapsed. So this is the problem of investing in blockchain money building concepts. But it is used for storing. Blockchains are used for storage, but for the any money building transaction like Sorota, this is not a useful task. What is data recovery? So it is a method of storing the database to its current state in the event of the failure at the time of transaction and after the end of process. Depending refers to both the flexibility of the database management system to various kinds of failure and its ability to recover from its failure. To gain a better understanding of the possible problems you may encounter in providing a consistent system, you will first learn about the need for recovery and its types of failure usually occurs in the database environment. What is the need for recovery and data? What is the need for recovery? So, the storage of data usually includes 4 types of media with increasing amount of reliability: the main memory, the magnetic disk, the magnetic tape, and the optical disk. Many different forms of failures can affect database processing and an or transaction, and each of them has to be dealt with differently. Some data failures can affect the main memory only, while others involve non-volatile or secondary storage. Or among the source of failure are due to hardware and software errors, the system crashes, when ultimately resulting in the loss of main memory, or the current loss or the power loss, and no backups. Failures of media such as head crashes, unreadable media that results in the loss of portion of secondary storage. There can be applicable software errors such as logical errors that are assessing the database that can cause one or more transactions to abort or fail. Natural physical disasters can also occur, such as fires, floods, earthquakes, and power failures. Carelessness or unintentional destruction of data or directories by operators of users, damage or intentional corruption or hampering of data or hacking, like miscellaneous software or uh, files, hardware and software facilities. One of the grounds of failure, that there are two principal things that you have to consider. Failures of main memory, including the database buffers, failures of the disk copy of the database, recovery facilities. Every database management system to offer the following facility to help out over the recovery mechanism. Next, backup mechanism makes backup copies of the specific interval for the database. Logging facilities keep tracking the current state of the transaction and any changes made by the database. Checkpoint facilities keeping track of the current state of transaction, any changes made in the database. Checkpoint facility allows updates of the database for getting the latest patches to be made permanent and keep secure for vulnerability. Recover manager allows the database system for restoring the database to the reliable and steady state after any failure occurs. Log-based recovery. The log is the sequence of records. Log of each transaction is maintained in some stable storage so that if any failure occurs, then it can be recovered from there. If any operations is performed on the database, then it will be recorded in the log. Both the process of storing the logs should be done before the actual transaction is applied in the database. Let's assume this is a transaction to motivate the city of a student, then the following logs are written for this transaction. What is transaction? When the transaction is initiated, then is write start log, that is in start. When the transaction modifies the city from Naida to Bangalore, another log is written in the file in city Naida to Bangalore. When the transaction is finished, then it tries another log and indicates the end of the transaction. That is in commit. There are two approaches to modify the data. Default database modification. So deferred database modification, the deferred modification techniques occurs when the transaction does not modify the database unless it has committed. In this method, all the logs are created and stored in the stable storage and the database is updated when the transaction commits. Immediate database modification technique occurs if database modification occurs while the transaction is still active. In this technique, the database is modified immediately after every operation. It follows the actual database modification. Checkpoint. The checkpoint is a type of mechanism where all the previous logs are removed from the system and permanently stored in a storage disk. The checkpoint is like a bookmark. While the execution of the transaction, such checkpoints are marked and the transaction is executed. Then using the steps of transaction, the log files will be created. When it reaches to the checkpoint, then the transaction will be updated into the database and till that point, the entire log file will be removed from the file. Then the log file is updated with a new step of transaction, the next checkpoint, and so on. The checkpoint is used to declare the point before when the database management system was in the consistent state and all the transactions were committed. Recovery from checkpoint. In the following manner, the recovery system recovers the database from the failure. The recovery system reads log files from the end of the start. It reads log files from T4 to T1. Recovery system maintains two lists, that read list and undo list. The transaction is put into read list if the recovery state sees the log with in start and in commit and just in commit. The redo list and the previous list, all the transactions are removed and then redone before saving their logs. Deadlocks in DBMS. A deadlock is a condition where two or more transactions are waiting indefinitely and one another to give up logs. Deadlock is said to be one of the most feared complications in database management system, and no task ever get finished and it will be waiting state forever. For example, in a student, transaction T1 holds the log in some rows and need to update some rows in the grade table. Simultaneously, transaction T2 holds logs in the some rows in the grade table and need to update the rows in the student table held by the transaction T1. Now, the main problem arises here. Now, transaction T1 is waiting for T2 to release the log, and similarly, transaction T2 is waiting for T1 to release the log. All activities come to halt state and emerge in the standstill without any operation. So this it will be remain in the standstill or a long pause until the database management system detects the deadlock or aborts one of the transaction. Concurrency control means the multiple transaction can be executed at the same time and that interleaved logs occur, but there may be changes in transaction result to maintain the order of execution of those transactions. During recovery, it will be very difficult for the recovery system to backtrack all the logs and then start recovering. Recovering with concurrent transaction can be done for the following four ways: interaction with concurrent control, transaction rollback, checkpoints, restart recovery. Interaction with concurrent control. In this schema, the recovery schema depends greatly on the concurrency control schema that is used. So, to roll back a failed transaction, we must undo the update performed by the transaction. Transaction rollback. In this schema, the rollback a failed transaction by using a log. The system scans the log backward to failed transaction. And for every log record found in the log, the system restores the data item. Checkpoints is a process of saving the snapshot of the application state so that it can restart from the point in case of failure. Checkpoint is a point of time at which the record is written onto the data base form the buffers. Checkpoint shortens the recovery process. When it reaches the checkpoint, then the transaction will be updated into the database. Until that point, the entire log file will be removed from the file. Then the log file is updated with the new step of transaction till the next checkpoint and so on. The checkpoint is used to declare the point before which the database management system was a consistent state and the transaction were committed. To ease the situation, checkpoints concept is used in most DBMS. In this schema, we use checkpoints to reduce the number of log records that the system must scan when it recovers from the crash. In the concurrent transaction processing system, we require that the checkpoint log record be in the form of checkpoint, where L is the list of transaction active at the time to the checkpoint. A fuzzy checkpoint in the checkpoint where transactions are allowed to perform updates even while buffer locks are being written out. Restart recovery. When the system recovers from the crash, it constructs two lists. The undo list consists of transaction to be undone, and the redo list consists of transaction to be redone. The system constructs the two lists as follows. Initially, there are both empty. The system scans the log backward, examining each record until it finds out the first checkpoint record. So that is the end of according to the syllabus, but still some few points to be discussed. So let's have some other features which is not in this syllabus, but let's we have to discuss later. We have to discuss in the coming section so that we can have a concept of these transactions in a detailed manner, which some points have not been touched in the syllabus. That is for our understanding. So let's see in the coming sessions. Thanking you for today.